Okay, so welcome everyone again. Today we are going to start our technical PhD seminar series on the so-called this semester on machine learning and data streams. I started these seminars in last year. Now this is going to be the third semester, but I'm going to mainly repeat the topics that I have been presenting before, and we have around 20 different topics to talk, but I will choose this semester. Let me tell you something more about these styles of seminars. Actually, there's a course you can register, and then you can get the credit for that if you want to attend to all the classes. But in principle, just think about this place as a kind of gym that we want to talk about topics, and then we want to discuss actually. And of course, 80% of the time I will be presenting, but I would be very happy if you have some comments. And usually when, for example, in some topics we have always very nice discussion. And I checked with the audience last year. I think mainly these discussions are becoming interesting at the end. So this is about a hot topic that you might know already, I guess, which is about machine learning and data streams. And you can call it big data as well, but I tried not to use this keyword. And this has been the topic of our chair at the CAAD for the last, let's say, 5-6 years. And I'm not an architect, and I have been working on this topic. I'm a systems engineer originally, but nevertheless I have my PhD in architectural department here. So today I'm going to mainly introduce this topic, and then at the end I will tell you what are the main topics that we are going to talk about it, and techniques and so on. So let's start first with the idea of how we see and how we look at the machine learning and data streams, which is a hot topic nowadays. This has been mainly part of my PhD research to try to somehow categorize and sort out the current situation we have around computational modeling, with a focus on urban systems. So because if you're familiar with this field, in principle we have a lot of names and keywords about different techniques and so on. So it's always becoming somehow arbitrary or chosen by someone else that you are working on some topics. For example, if you start on, I don't know, building energy, you hear that, okay, everybody uses CFD. Why not? We should use CFD. And then that's it. If you work on traffic, you say, okay, let's start working with agent-based systems or cellular automata because they're cool topics. If you work in economy, you might start working with econometrics, for example, but you don't know why. And this has been, I think, my questions, because I have been from outside of this field. So I've been always interested to know, because, for example, if you start on, I don't know, building energy, there's a problem, I think. Sorry, on the other side of the Skype, can you please turn off your microphones? I think there's a problem with that. No? Okay, now it's perfect. So this has been the topic in principle of my research, long-term research, that I try to categorize and abstract these techniques. So I will not mention a lot of them, but there are a lot. I have a list of, I can say, around more than 100 different concepts, and then I call them great concepts because all of them are great in their own times, and they have all life cycles. Like deep learning, if you have heard today, now it's a hype around it. Machine learning is a hype around it. But if you look at this in the time domain, in like 100 years, you might see it has like a lifetime. Like it goes up and it goes down. And then if you are just opportunistic, you just take it and use it for your method. But my research mainly is about this method. So I'm trying to be abstract. I don't focus on specific applications. Nevertheless, I work on different applications that I will show you. So if you look at the history of computational models, and this is going to end to machine learning and big data. This is a working model that we have in principle. These are the y-axis is the capacities for modeling. So in principle, we have analytical models. So like Newton's equations. We don't need computation in principle for Newton's equations because, for example, you can find answer for that directly analytically, and then you have in principle a closed form answer for that. Or the way we learn at high school mainly how to solve equations, systems of equations, you can solve them analytically. But in many applications, we don't have closed form systems or closed form answers, and then the analytical answer. So this was the main challenge during beginning of 20th century. And then it ended up to the notion of computation and then numerical methods. So if you think about origin of computation, I don't want to go to history, I just want to be fast. Computation, you start always with mainframes. So this is correspondingly to this kind of closed form models that you cannot find the answers, but you can simulate. This is the case, for example, in most of computational fluid dynamics cases, and in principle most of systems of differential equations. Just think about it, that you have an idealized models of particles in the air or wind or water or whatever, but then you don't know what happens. You want to simulate the flow of water. So you have the equations, but you don't have the final answer. So you need to have a notion of time, and then you have the notion of discrete simulations. So you just start simulating this numerically, these equations. So you just read these equations over time. And this was the beginning of, in principle, simulation for me. So then this correlates a lot with the notion of mainframe computer. And then later we had these notions of, during 1970s, 80s, you have the notion of PC or personal computers, and then gradually we have the notion of networks. And then this correlates a lot with the notions of internet, PCs, and correspondingly to the modeling domain, it corresponds to, if you're familiar again with agent-based models and cellular automata model, for example, that in principle you don't know any longer an equation for the system. For example, in the case of water flow, you have an overall equation. You just say, I know this is the way particles work, and based on gravity, frictions, and density, and many other factors, but you don't know the answer. You always start with the initial condition, and you just read the equations. In many cases, you don't have these equations at all. So you just say, I have local rules. I know how people might walk in the street, or I know how there are regulations, local regulations, and then you just have this kind of decentralized or distributed models that you are expecting to see the emergent effect. And this is correlating a lot conceptually with the notion of internet, because it's not any longer about the computational node, it's about connection of the nodes. So just as a picture, you can see here, for example, as a centralized models, we have this kind of very powerful CFD models, and it's a big field. And actually, I think in architecture nowadays, we are using these techniques as well. But they reach to a limit, for example. They have a limit of computational complexity. So they are idealized, and they work only small scale. If you increase the scale, the demand for computation increases exponentially. So always these models are in a catch-up process. And because of that, yeah, it has been always a hope from these people who are in this field to say, okay, one day we have better computer, and then we do it better. Because the models are in a way valid. For example, if you want to, for example, one case that I'm involved at the moment is that there's a problem of water flow simulation, and at the end you want to predict the flood risk at the building level in a city, for example, in the catchment area, for example, Luzern. You want to say what happens if it rains 10 minutes from this location. So if you want to simulate this with a very fast method, with this approach, it takes 5 days to tell you what happens if it rains 10 minutes. So it's valid, but it's not working. So it's a computational problem. And if you add one more feature, for example, now we say, okay, I want to include the effect of vegetation. First of all, you have parameter tuning, and second of all, the demand for computation again increases. So it's always a catch-up game. You start with a rule, which is correct sometimes, but you can't simulate it. In the other cases, that is a kind of decentralized models, you dissolve this problem, and you just say, let's think about agents. Let's think about now particles of water, not about the global equations of how water flow, but about an equations of how these particles are competing with each other. So now you can say that we have now local rules. They push each other, they attract each other. If there's a gravity, they get faster, they compete. So you can see that you can actually use this kind of thinking in many fields, like in cities, in economies, in the flow of money, and so on. But again, you have always these assumptions that you need to start with the rules, either a global rule in terms of equation, descriptive theories, or in terms of local connections. So there has been a lot of work during 1960s to 80s about this kind of thinking in for example, in cities and architecture, and there has been a lot of catastrophic cases because they assume that, for example, people would walk like that, and then you make a lot of simulation. At the end, you say, okay, this is the best design because I think by that, if a fire happens, this will be the way people will walk. And there has been a lot of mistakes in these kind of assumptions, because when this fire actually happened, then people realized that, oh, no, it was not correct. So what happens now? People couldn't go out, for example. This was a case, I think, known as Rand Corporation model in, I think, during 1970s. And before that, for example, this was a fascination at the cities. For example, people were using Newton's gravitational rules to model land use dynamics of the cities, how people are attracted to do different things, because there should be some forces, and then based on that, people do different things. So, but nevertheless, they are all interesting topics, and I will show you that I'm not against all of them, but the important thing is to know the limits and the locations and the positions of these things in these abstract environments, and then if you know them, you are kind of literate in computation. And I think the main critic I have, I think many agree with me, is that, for example, in architecture and design, this computation is everywhere, but the use of these techniques is just the use of the techniques mainly. So in principle, people, I have seen in the architectural conferences, people are interested in agent-based models because somehow it's cool. So you can connect it to many of the other things, like it correlates again with ecological thinking, it correlates with sustainability. I don't want to go to this field, but you don't know the limits, for example. And then I've seen many times that people say, scientists says this is the way people walk in the city, and this is the way people drive in the city. So based on that, you build a simulation, and this is one layer of your simulation, and you just say, now let's decide about the optimized layout. This is the wrong setup, because you don't know about the validity of your models, and then on top of that, you're trying to optimize something. So that's been the problem. But nevertheless, I think Mr. Wolfram is doing very interesting research on this cellular automata, and then he has a lot of rules. I think you should check it out. And for example, these kind of patterns, what's going on?
By YouTube, so.
Ah, okay. So, even better. So, in principle, now, for example, this is the way I told you about this notion of emergence, for example. You start with these rules, and this is called rule 30. So it says if the pattern is like that, the main cell is become like that. If the pattern is like that, the main cell is like that. You start like this, and then you end up to this kind of patterns. So this is the so-called local to global, or the notion of emergence. And then, of course, you can do more complex things, and then you beautiful patterns you can generate, like these. They're all cellular automata patterns. And then, as well as I told you, you can think about these instead of having equations for flow of anything. For example, you can think about local rules. So, for example, this is a model for flow of water, or in principle, if you know the local causalities for movement of particles, for example, you can make the same thing. So, for example, these are the area that you want to model, for example, for flow of water, for example. So you just say there should be some relationship between these cells. Most likely they are just interacting with the neighboring cells. This is the case of cellular automata. So you say if there's a vector of this, each vector, for example, could be the vector of flow of the fluid, could be water, for example. So you just say where is the gravity direction, and then based on that they're moving. So you can make very interesting simulations, and most of the time for idealized setups, mainly for physical systems, valid. So, but nevertheless, this was kind of introduction to go to the third level, which is here, and I didn't tell you about it, which is this notion of data streams, and this is our focus in these seminars from now on. So after this kind of computational networks, and then abundance of, in principle, computing everywhere, nowadays you have a notion which is called ubiquitous computing, or sometimes pervasive computing, which means computation is everywhere. It's not like classical ways that you say, I want to design something, an experiment, and then I use the computer. Computer is part of our daily life. So the data is being produced by this ubiquitous computing is not any longer designed data. is a data which is coming from different activities. For example, we are walking, and then our GPS is on, so we're having these traces of our movement. So this is a kind of data, and then it creates a big data if you are using Google, for example, map. Or for example, we are using social media. We are leaving a lot of I would say footprints or behavioral prints behind ourselves. So these are becoming the notion of big data, and I call it data streams because they are very for a short time and for a specific kind of locality or temporality. So if we know how to deal with these data sets, this is the idea of data-driven modeling. And here the beautiful thing is that, for example, I don't have this slide now, unfortunately, but imagine now this is an idealized model of how traffic would work in the city, for example, how people and how cars would work, and how they would people drive in the city, and this is the patterns of people. So there have been a lot of theory-driven models that they were trying to say what is the, for example, the logic of people from moving from this part of the city to other side of the city. So you make a lot of agents, and then it's called multi-agent systems, and you just try to simulate the traffic behavior of the city. And then you have very few data set you want to, validate. But here with these data streams, now imagine, now we have these movements, real data set from our movement, and nobody knows why I'm walking like this in the city or why I'm moving like this. Maybe I might be, as a person, very rational, so I'm taking the shortest path. Sometimes I'm not taking the shortest path. So whatever is the rule, it's embedded in these data streams. Now we need a new kind of mathematics, a new way of computational thinking, which is called machine learning, that is able to deal with this data, because this data is not design data. Sometimes we don't know the attributes of this data, but we have always a certain goal. For example, we want to mimic the flow of the traffic, and then we want to do some kind of small interventions, but we don't know why, unlike the other methods that I told you, we don't know how and why people are behaving like that. And in principle, you are trying to forget about this question of why, because you know what is happening in principle. So here there is a major shift, and I think this shift is from the notion of theory-driven models to data-driven models. In principle, in all of these previous examples I told you, you have always a logic or a rationale about the system. This could be flow of water, flow of cars, land use, any application that you name it. So you start with this, and then you compute it, or you either have it, I don't know, analytical models, and then you have always certain observations, and then with this observation you try to validate your logic. And if it's correct, you say, okay, it was correct. With this kind of data-driven modeling, you forget about this logic and rationale, because in many cases, in complex setups, you don't know the rationale. And for example, as I told you, for example, traffic, or for example, one very maybe interesting application would be natural languages. For example, the way we are talking. This has been a main topic in this field for a long time, that whether we can write down the rules in terms of semantic and syntax, how, for example, we can model language of English, for example, or German, for example. And is it possible to model this in a computational way? So if we can do it, so in principle we should be able to produce a correct language. And it has been always a failure, because always you started with a model. You assume that this is a grammar, and then you always say, look, this is a grammar, but there are infinite number of exceptions that you need to learn. But these models, these computational models that I told you, so far they just know that they should start with a rule. So if you say there is this rule, but these rules are changing immediately, this model can't be working. But as a breakthrough, for example, nowadays we are all using Google Translate is not based on this kind of grammatical model. It's pure data-driven. So in principle, it learns whatever is the rule embedded in the data. And that's the whole tricky part with the machine learning. And I think we are going to repeat this topic and this sentence, that you should stop thinking about how and why. And if you don't do it, it always gets tricky, because this is a different kind of thinking. And this is a shift in the style of scientific modeling, for example. So that notion of translation. We have now these successful applications in natural language translations. That, for example, I told you, I will tell you this. I will tell you about this natural language translation in next sessions in detail about the algorithms, and you should be able to use it as well if you like, as a kind of end-to-end models that you just learn a sequence of words, for example, from German to the sequence of the word to English, for example. If you have a lot of them, and this has been not the case here before 2000, let's say 10, because we didn't have a lot of data. Nowadays we have a lot of data, and it's called big data. By that you can encapsulate all of these rules, and that's the whole idea of machine learning, how to encapsulate rules without explicitly saying what are the rules. So we should forget about the rules. So for example, again, a very arbitrary question: how do you design a comfortable buildings? For example, this could be a question for those people who are working for, I don't know, building energy or building physics, because they always start with the notion of comfort. They say, okay, this is the temperature that would be interesting for, of course, for our natures, and then there is no CO2 emissions and so on. But how do they know what would be the reaction of the people? And if you start with those models, at the end you end up that, for example, most of the smart home applications doesn't work because they assume a generic and idealized user or the person who is living in the house. And then when you are going to the operation, I think I don't have internet any longer. Okay.
I'm not following by YouTube, that's why they...
So, okay. And Luther, I forgot to call him. Let me see if he's, sorry. No, the problem is I don't have internet, I think, no. Oops, okay, he's not. It's okay, he knows it. So the problem is that if you start with these models, you have a logic, how should be a good temperature, for example, how is a good range of temperature and so on, then you design everything on that, and then people come in and say, okay, this is not interesting, so it's a problem. So we have a lot of these kind of examples and in different fields, and it's amazing because for me as a systems engineer, I have been working in a wide variety of fields. I will tell you about these applications. I'm not just focused on architecture, and I'm not architect, and I'm not trying to claim this kind of research in architecture, but there are infinite number of applications, and this is beyond just architect. It's cross domains. So it's a new way of thinking, and for me this is very interesting topic for at least for next 10 years, because now I go to every field. I'm trying to collaborate with different people, and I see there again the same concept. Like you start with this model, and then you say, okay, what if this model is not correct? So what do you do? Nothing. Okay. Sorry for that. So, and there are many of these applications, and I don't know if I should go to this part because it becomes again a bit abstract and you might not like it if you don't. But with these kind of data-driven models, we have a major shift, as I told you, and then there are further major changes. For example, we have the notion of idealization in classical scientific modeling. Always when you start, I don't know, about anything, when you talk about water, cities, a building, you always start with the notion of a generic object, for example. And then you idealize this. For example, you just say idealization means, for example, you just remove the specific things. For example, you just think about the solar systems. It's an idealized image that we have, that these particles are just turning around each other. This is like just focus on a specific feature. And in this, and then for example, for movement of people in the city, you just assume that people take the shortest path because you say people are smart. So this is a kind of idealized person. It's not that real person. What if the person is drunk, for example? Is not included in your model. What if the person wants to just drive, just for fun? And this is, for example, very common in our country, in Tehran, because oil is very cheap. So people always drive. So it's cool, huh? And then you just race and this kind of things. You should see this. So here there is no model for that because this is out of this idealized setup. Or in principle, there is another problem with this kind of theory-driven models in complex setups, that you can't integrate them. And this is a theoretical problem. For example, now there are a lot of work on this kind of interdisciplinary research. For example, for something which is interesting for me, in the cities, for example. Classically, you have a silos of models for transportation, and then you have a department for that. You have a department for energy, and sometimes you call it building physics. And then you have one department for, I don't know, social aspects, one department for this, and then correspondingly for all of them you have models. So now, recent years, because of availability of data and so on, we have these kind of research programs everywhere, including ETH and master programs, that they want to integrate these things together. But they can't talk to each other because they're from different worlds. You always start with these models, and these models are not able to integrate. For example, you want to know what is the effect of, for example, there is an effect called urban heat island. And there are a lot of factors are affecting this heat island. But then when you go to this kind of research questions, always there are people related to material and concrete, people related to the car industry, people related to traffic, people related to the land use and so on. And then if you want to integrate these things together, it only becomes a kind of complicated models that you can't validate, because there are a lot of open space in between. What happens if a person is driving like this and the car type is like this? And then the person even is cooking at home a lot, so it creates a lot of heat. So how do you want to model these things? So this is a notion of representation, and most of these models classically are representational. So in principle, we want to mimic the reality of water. So in principle, it can't be. So it's always some kind of limiting. And then if you go to more complex and not necessarily physical systems like cities, for example, you have a lot of factors. So you can't represent the city. And this way of thinking, which is starting always with the rational and logic, which is helpful in many applications like design applications, is failing here. And this is the notion that now we need to use the concept of end-to-end models. So this is a bit scary for those people who are interested in theories and they want to know why and how, which is a good question, I think. But at the moment, I think in our time, I think never, but some people say for now, we don't have a solution for that. So the idea of end-to-end models or targeted models is beyond this concept of generalizations and these global models. For example, Newton made his contribution, and now we use this kind of models for everywhere. But if we go to specific cases and more complex setups in many applications, we don't have this kind of generalization, and it doesn't make sense to make a theory out of that. But still, there are many people who are trying to make theory about the specific observations and so on, a specific case and so on, and try to generalize it. Here, we just say, forget about it. What is your question, for example? If you want to translate, that's it. You need to have a lot of data from two languages, for example, from English to German or any other languages. Or if you want to create a question-answer system, the classical way would be to think about the semantics of this environment. For example, if I say hello, you might say, okay, what should I tell in response? So if you imagine if you don't know the language, you want to model this. It's really complex. Here with this big data, you just learn them together. For example, you will see this later, is a model called LSTM. Is a kind of recurrent neural networks that I will talk about this in one of the sessions, and it's extremely powerful. And I have at the moment I'm working on this field and this method in the same, more or less same architecture, which is abstract, for converting one side topology diagram in graphic static to the other side is a form diagram. So this is that generic. You can go to any fields if you learn it. It's amazing. You can think about one side would be the green one would be the structure of a city. The other side would be how traffic would work in the city. And if you have a lot of data, you just don't try to first say, okay, how this is happening. You just try to fit them together. And this model learns to encapsulate whatever is the rule. And if you change your data, means that you have this kind of evolution over time, the model gets evolved. So you always don't know what is inside, and some people wrongly call it black box, but it's a kind of intellectual decision, because otherwise there is no answer for that. you can solve the problem. Here, for example, it says, how are you? These are called cells of these neurons, and then you have a notion of sequence. It learns that how are you? The answer should be I'm fine, end of line. So you feed these models with a lot of them. Now think about it that it can be a graph. You feed layers of a graph, and then you expect to see the other side something else, or anything, and it can be any applications, and I will try to show more applications in next sessions. So this is the concept of end-to-end or targeted models. So here you don't try to represent the language. You just say, what is my question? I want to make a chatbot, for example, in this case, that is able to answer logically. And then this logic means that in this context of this company, for example, you have a company, you have a certain product, and then you have a lot of question answers. You feed it to these models, and it's extremely simple at the same time. And this is why I'm very interested, because I can show you, for example, in 2 hours, you can make these systems running web-based. So you can make these applications for any case. And this is interesting. So here is a kind of application, but if you think about it in a classical way of thinking, it could be a research question. So this is why Google is very fast, because they have this kind of language, and or similar companies like Facebook or Google, and they go to any fields and they just say, okay, these people are trying to understand, and then we don't, but we have the big data. And this is not necessarily meaning that they don't understand, but it's a decision that you say here you can't understand. It's complex. So this is yeah, sorry, it was too long. I myself didn't expect to be this long, but I saw different new people, so I said maybe I should talk about this thing. Otherwise, those old members of our group, they know this kind of stories, but with this concept, in principle, I'm trying to provoke you, and then I want to be provocative, and I want to say that this kind of data-driven modeling is a new way of questioning in science. So I think this is a new language, and then you can talk science in a different way. So because of that, this has been my journey during the last 10 years. I have been always pushing to go to different fields, because I was systems engineer. I didn't want to focus on one field. So I think the proper language is this machine learning and big data. And before that, I was into, for example, general systems theory and system science, which simply doesn't work. But nevertheless, this notion is adopted from, for example, Bertalanffy or George Clare. This is Bertalanffy's 1940s or something like that. They visioned, what if we can find some ways of looking at these seemingly different disciplines, and then we can standardize them. And the problem was that they make this again system models, and these system models becomes useless in principle. And this was, I think, in my opinion, end of system science or systems engineering in 1980s. But now with this machine learning is again evolving, because now I can claim, if you have any problem, just bring it here, we can talk about it, and then we can attack it with this way of data-driven modeling. And I've been doing this for now last 6 years at least. So in principle, these are any fields. These are arbitrarily chosen labels: urban forms, economy, energy, infrastructure, transportation, water, climate, people. In this way of machine learning or data-driven modeling way of looking at these problems, you always see similar problems, similar questions. And then you can use other use cases. For example, if you have developed a model for detecting buildings from satellite images, the same model have been used to detect cancerous cells in, for example, in medical imaging, because more or less they have the same context. So it's open. So if you like it, you will find similar things. But it depends a lot on you, because I like this way of looking at different fields. But if you don't like it, it still is fine, because you might say, okay, I like to focus on energy, so I don't want to go to any fields. I like energy for itself. That's fine. You can. I'm pretty sure you can approach these problems in urban energy or in building energy or whatever energy with this way of looking, which is orthogonal. So in principle, you need to learn machine learning, statistics and probability, optimization a bit, linear algebra, and data science skills, which is in principle hacking, how to download the data, because most of this data doesn't exist. So you need to find data sets. For example, for one case, for real estate, a case that I developed for, and then this is going to be a company hopefully soon. We are crawling all of the existing real estate portals, so we get a lot of data from advertisements, and it's for free, but you need to know how to get this data, because if you go visually you can get it, but you need to write a crawler. If you get it, then you have a big data. So if you have big data, you can use machine learning to predict the price. And then, for example, we quickly had the 95% prediction of real estate price for buildings all over Switzerland for rents, for example. It's easy. Or you can ask this kind of question, and then I develop an application for the first time, web application. Now I will show you in one of the sessions. Or for example, OpenStreetMap. In my case, we are interested to use to know the urban forms, and this is the field of urban morphology. Classically, it's always based on few cities, known patterns, and so on. But with OpenStreetMap, you have around 1 million cities, all indexed. So in this case, we downloaded all of this data, we converted all of this street network to one picture for each city, so we have 1 million pictures. And if you learn this with machine learning to learn these topological similarities, it gives you a nice pattern of urban forms, which is not based on any theory. You just say this is the case. So you can create a search engine of urban forms, or you can create a search engine of floor plans. Now, for example, it's easy to just get data from floor plans up to 1 million floor plans. But then you need to know how to figure out how to play with this data. So this is the data science skills, and always data comes with the structured data sets like CSV files and so on, or text data, image data, time series data, and network data and graphs. And so machine learning for me is a language, and it's evolving. So I don't know how to, if you want to learn it, I don't know how would be the structured way. And I think definitely there is no pedagogical way to say, okay, start this and this and this. And I think the best person in this field, or the most famous person, Jeff Hinton, who is now godfather of this deep learning, recently he had an interview and he said, if you want to learn something, never take a course, just get a professorship for that topic and then do it. And this is the person who changed a lot this field, and he never took a course in, for example, machine learning himself. So I want to say that if you think about this big data, all the materials about big data and machine learning should be again big data. So you should be able to learn easily. You should not just focus on a specific theory. I mean, what I tell you is my story. If you stick to it, it's again kind of theoretical or rule-based way of thinking. So you should, and this internet is full of resources. So you can learn a lot. You can go to different courses. You can take online courses like Coursera, Udemy, and many of them, or you can play with these codes. And this is the notion of, I call plug and play machine learning, because if you search like in 10 minutes, you can find how to start from scratch and build a chatbot, for example. There is always some data set. You can develop a model, train your model, and then put it online, so it's working. If I write something, the model answers. You can do it for image segmentation. You can do it for, I think in principle, self-driving car should be the same in principle, because it is a kind of end-to-end model. So then in principle, I think there is no pedagogy, but you need to learn a bit of structure and grammar, like any other languages. You need to start, but it's not just structure and grammar or language, the keywords, but you need to learn these words and so on, exactly like the way you learn a new language. So I will talk about these things. I guess if you are not interested in these techniques, sometimes it gets boring, but I think it's important. For me, it's important to learn, for example, basics of linear algebra, what is matrix calculations, what is matrix operations, so on. And if you don't know it, you become again some kind of end user of these technologies. You need to learn that. So a bit of optimization, a bit of probability theory, and we will go through them. And there are a lot of algorithms. And then at the same time, you need to engage yourself, if you want, by a specific case. I think this is the best way. You should find a specific problem, and I'm pretty sure in any field you can find it. Or if you are interested, really, we can discuss, because I would be very happy to find new problems. And then you learn these techniques by that specific case. And then at the same time, guessing, hacking, and copy pasting. This is extremely powerful. You need to learn like that. And you just need to copy paste and then you say, okay, what is this? And then you change it a bit and you learn it over time. So it's a kind of pattern. And there are a lot of keywords. I tried to put them in these 20 slides, 20 different presentations that you have it already online. And I'm going to continue in this direction. There are a lot of topics. What is reinforcement learning, supervised learning, unsupervised, and so on. And there are many techniques that you can learn if you like. I know them, for example, this, but it's not all of them. So this is kind of my keyword that I like to here show off in a way. So, but it's not necessarily important to know them all if you want to do it. So I think I already mentioned a lot, but I hope I can. These are the main applications that I have done it either, or I've been doing it now. For example, design space exploration. In this case of structural engineering, I'm doing this with a group of Joseph Schwartz and with Ole and Pierluigi. That you want to learn what is happening from one side. That you have this topology diagram, which is trying to find the equilibrium. And then from the other side you have form, because you might end up if you simply generate a lot of forms which are all in equilibrium and stable, they are not beautiful, for example. They are not harmonic, for example. So it's easy to generate a lot, but you don't know what should be the parameters. So the way currently is being happening, based on my understanding, is that it's a trial and error, and then you should guess, for example, and you should have an understanding. And it gets very hard, in my opinion, because you have a new notion. For example, now you have force diagram, for example. You should learn how it works, and this is the way in graphic statics. Now the question is that is a kind of when you can generate random variables and then it gives you a form, but this form most of the time is very ugly. So the question is that if you think about it like a gold mine, can you find these areas of gold? Because everywhere is full of garbage and not interesting things. But there are those interesting combinations that create those beautiful, for example, domes, for example. I can show you this later, but we don't have a result for that. And here again, think about these layers of your graphs, again like these patterns that I told you. And here you have force diagram, and then we expect, I should not claim it, we don't know yet, I need to implement it. And then from the other side you have form. So the question is that, is it possible to learn to generate gold? Not everything. So this is very risky. I know if you're an architect you might hate it. So, but I think this is the idea, because in principle this space is very large if you think about this combination of these variables. And not always you have this harmony. So with computation, we can learn to search in this space. This is the whole idea. And then in principle, for a while I was interested in this, but I never did application on this computational drug design, because then now you have in chemoinformatics, for example, you have combination of molecules, and then you just say it's a good drug or not, for example, it's a very simple way. So you have these simulation models, but you don't know the final results. Again, similar to this structure, is it possible to learn which area of this space is producing good, for example, drugs? Something like that. And this is, I know there should be, I know at least 2 departments at ETH only that they're working on this. So then I've been working on different applications on cities, like urban morphology, and many others, like Diana is working on this topic, more or less Carla is interested. And in the city level, you have a lot of data, you can ask different kind of questions. So there is another topic which is very interesting, which is called data-driven simulation. As I told you, these CFD simulations are very slow. They can't scale up fast. So you need to learn them. In this case, there is no big data, because there is no data for flow of waters, for example. But you can use this data of your simulation as your training data for models, and then train. And this is called learning physics, and it's becoming very active topic in my opinion. For example, in computer graphics and animations, because you need to be fast if you want to have a flow. I will show you a picture of that. And then in case of urban economy or real estate market, I will talk about this one case, the full stack developments that I did for real estate market, from getting the data to telling a certain story. And then now we are talking with some investors but it's not working yet. Hopefully it will be a spin-off, but not yet. Then network and systemic risk, though I have worked on these cases, I will try to present it in energy networks, and then flight networks, economic networks, and then transportation networks. They are from seemingly different fields, but if you look at them as a flow of something in a network, you can use a lot of methods. For example, here we use Markov chain as a systemic risk, for a systemic risk, to come up with systemic risk. But I will show you this in detail, don't worry. And then, yeah, many other applications. These are more related to my master thesis. And then natural language modeling applications. I think this should be very easy, and we can show you how to get the data, for example, from Twitter, how to use some kind of sentiment analysis. For example, one application that I'm pretty sure if you want, you can do it in maybe in short time. For example, Donald Trump is tweeting, but do you know how many people like it, how many don't like it, for example? Because if you go with like, I don't know, 100,000 comments, so you read the 10 first, and then you say, okay, I think people hate it. But then you don't know, maybe there are other people who like it. So there's a question, there's a business application for that. It's called public opinion mining. So for this kind of simple applications, if you have a new product, you want to know how people think about it. So you need to have a lot of training data, and this is like a review of something. And then you have these reviews, and the answer is yes or no. And then you have a lot of that. So you need to make it automated. This kind of applications or topic models. And for example, Jorge Orozco was working on this topic and this notion of images and text data a lot. So atmospheric science, I've done recently one applications, which is, I can show you later. And these are in principle, I just want to tell you that these are the topic or subtopics of the sessions that we are going to talk. So at the end, I wanted to show you, because I had a lot of preaching, now I just want to show some of the applications. For example, this is a case that now you can use it. The code is ready to use. Like, it's just a small amount of code that you need to learn how to import a library, and that's it. And for example, this is a real-time semantic labeling. A person is biking, and then at the same time the camera is labeling everything. I don't know if it's visible for you, but it detects everything. So it says this is road, this is a person, and so on and so on. So imagine this is for labeling, but for self-driving car, even you don't need this, because you need to learn it end to end. So in principle, you need to look at these pictures, each frame, and then decide what should be the angle in the steering wheel. You don't need to know the mechanics of the car. You just need to behave like a driver. So you need to put the camera here and then drive for a long time. And then you are collecting a lot of frames, and then these angles and gas or something, other things, and brake. And the model learns this as a good driving style. Maybe it's a crazy driving style, but it learns it. If you add a lot of drivers, it learns by that, and then decides on top of that. And this has been a problem for many years, because now it's working with this kind of deep networks that I will tell you in at least 3 sessions. So you can easily label these things. And for example, I'm using this problem with a collaboration with DLR in German Aerospace Centers, but I just started last week and it doesn't work because of, I think, resolution of the pictures. But here we have a lot of image tiles of certain areas in this world, and then we want to detect where are the informal settlements. If you look visually, you might realize that here is an area, but if you want to do it automatically, that's a hard problem, because you have pixels, this is the only information you have, and then you have some labeled data. So the question is that, can you label the pixels? And this is exactly the same problem as here. Here you just label the pixels. You just say this is a label of road, and here you just say this is a label of formal settlement, this is a label of informal settlement. And then the same thing can work for medical imaging, and this is the case. Or a lot of interesting applications in digital humanities. I don't go to these applications because it will be long, but I will upload these files and then you can look at it. For example, here you have around more than 200,000 woodblock prints, Japanese artists. And then you can use again some kind of machine learning for indexing, and the results are very interesting. For example, now you can make visual queries. For example, you say which picture is similar to this, and the results, for example, something, I think this application, for example, if you look at this, it gives you these results. And if you think about it computationally, how you want to do that, and it's just the picture. And this has been a lot of work for, I think, for 30 years. So these people who are working in this field of computer vision to develop these methods, that we will talk about them. And now it's working. For example, I do the same thing for cities, for example. Now these are is a kind of dot map of 1 million cities. So we have 1.1 million locations. We go to each location, we take a photo of a street road network. So it looks like this, each frame. Okay. Sorry. So the resolution is not good, but each frame is a city. So the question is that, can you find similar cities without using the rules? If you know this field, for example, it's called urban morphology, people start always with the generic archetypes. Here we just say we don't want to use archetype. We just want to know for this city where would be similar. And this is just one layer. It could be anything. It could be prices, it could be the types of people. And if you have a lot of data, you can train them all together. So then, for example, you get that. Sorry. And then, for example, you can make this kind of visual queries. For example, this is a query, and the system tells you these are possible patterns. So you don't know where they are, but they are real cities. And I will tell you in detail what is the conceptual change here. That they are not synthetic any longer. It's kind of indexing the word. And if there is a dynamic that we don't know why this is happening, we don't try to start by that. And then in principle, if these cities are changing, our model is changing. So it's you appreciate the complexity of the word. In principle, planning is a complex process, but we don't try to say what is the planning and why and how it should happen. We just try to index the reality. And then think about it that at the moment you have these pictures, and I'm from the other side, I'm collecting, for example, air pollution measurements. So then you can ask very targeted questions. Can you look at the area with satellite pictures or something and then say what would be the expected pollution, for example, without a model? And if you have a large area, like 8,000 locations in the world, it gives you a lot of generalization prediction for many other areas. Because again, for example, in that case, the problem is that you can't measure everywhere. So one interesting case from, for example, Disney research, ETH, this is a kind of data-driven simulation of water, and it's in real time. So it's very fascinating, and it's based on a method called random forest. So the data is coming from a physics-based simulation, which is very slow. It takes a long time to just get the data. And then the model learns to predict the next steps of any particles of the water. I had a meeting with this person who has done this project. It's very interesting. And I think they are, in real time, they're predicting more than 1 million particles locations. They just like, now all the particles, what is next step? What is next step? And then the result looks very good, because now then they have a lot of contribution animations and so on. But here they don't, here is again kind of representation, because they don't look at the final results, for example. In this case, for example, in a similar case, what we are collaborating with EVAG Institute is not to simulate the whole water flow, which is interesting in itself, but to just say what is the risk of flood at the end, for example. This is interesting for urban research, for example. And this is a very, very interesting work, and I really liked it. And so if you think about it, how you can simulate this, it's incredible, I think, this work. Or there are other cases like, I think these multi-agent systems, that there's a guy in Google Brain, I think he's doing very interesting works in a very fun way. So each of these guys are having their own models. They learn by interaction. So it is a trained model. If I add one line here, they detect, and in principle they have few features, like looking to the closest obstacle and then decide what would be their move. So by using this kind of neural network and machine learning, you can make these models and then they can survive. But again here, because it's agent-based, then the problem is that, for example, here there is no coordination, no communication, and it becomes a bit problematic. But this has started a new kind of wave in, for example, traffic simulations, that you have movement of car in high resolution in time and space, and then you learn these models by this, for example, recurrent neural networks, and then they learn how to simulate a city, then in principle, because it encapsulates all of these logics that we don't know. So there is another area that I think this is at the moment the hot topic, and at the same time bottleneck in machine learning, because most of the application that I told you about is mainly about kind of analysis, and then you don't have synthesis, and this is always a question: can you generate something new, or can you generate? And this is the way, for example, architects or designers would work. It's not just about analysis or understanding what will be the price of this house and so on. But is it possible to come up with a new thing? And this is the field of unsupervised, more or less, learning in machine learning. And this is, for example, very interesting, I think, very successful case. And here is a kind of interpolation. You have these two pictures on two sides, and the model fills in between. And now the question is that, is it possible to recognize, for example, which one is fake or which one is not? So we are at the time of fake news and fake pictures, but this is the state of the art. So from the technological point of view, this algorithm actually is called BEGAN, Generative Adversarial Neural Networks, Boundary Equilibrium, is comparing, this is the third row here, and this one is a kind of interpolation. And just think about it, that it's not interpolating pixels, it's converts them to a latent space, and there you have linear interpolation. Because of that, it's super powerful. So this for me, this is the work of, I think, 30 years of hard work of these guys, that they managed to convince the society that this method works. So now you have this kind of applications, which I think many don't like it, but it's working, and look, it's automatic, so you can generate it easily. And then, for example, just for fun, I saw it yesterday in the Twitter. If you take 25k 19th century portraits, results seems good. These people have never existed. So it's called kind of random pictures, but think about it, that it's generated automatically. And if you think about it as a high dimensional problem, it's extremely hard. I think the result is fascinating. Maybe this guy you might know, for example, looks like, I don't know, Abraham Lincoln or something.
Then you look like someone we should know.
Yeah, in principle. So there are a lot of applications going on in different fields, and for example, there is a very interesting comprehensive review on generative music, for example. Is it possible to learn the sequence of the notes, for example, or in terms of as a time series or audio and so on. So I read this quickly, but it looks very interesting, and it starts with Markov chain and early works in these fields, and then I just wanted to maybe just select one of them, which is like all, yeah, for example, this is seemingly generated by a recurrent neural network. Yeah, exactly that's the answer. At the moment, for musicians, they say it's horrible, and in principle, the problem is that it learns always in between. But in terms of looking at the difficulty of the problem, it's extremely beautiful, because it learns a long-term history. I mean, it learns that if something happened now, what should happen in 20 minutes, for example. And here, I think I will encourage you to look at this. I think this is a kind of crazy test. It's a musical Turing test that a real performer and the computational performer are competing. And yeah, there are lots of crazy things happening around this. And as I told you, most of the successful and convincing applications are those kind of analysis applications, like you want to predict something, but when you go to the generation phase, it becomes very tricky. And I would be very happy if you, because you're mainly designers, if we can in one of our sessions discuss, or maybe today after my presentation, because I'm going to finish it, to discuss and reflect on this, because what happens if, because for example, self-driving cars was crazy 10 years ago, and the interesting point is that these computer scientists, in principle, they don't care about the social problems, or in principle, self-driving car now has a social problem and social acceptance problem, because what happens if there is a crazy accident, or what if this driver becomes crazy, and so on. But then at the same time, that's the role of society to reflect. And I don't think, for example, we should stop this, because many people say, okay, this is ugly, you should not do this research. But why not? I mean, maybe it works. And if it's ugly, always people say it's ugly, which is fine. So, and this is a very, again, kind of new things. If just think about it, the complexity of the problem is a kind of face-to-face model. That
Since
now.
the method only uses RGB data for both the source and
Okay,
target
I don't know if you
actor,
want to
we're
listen
able
to this.
manipulate YouTube videos in real time. Here we demonstrate our method in a live setup. On the right, a source
It
actor
looks
captures
scary
the
for me,
webcam.
because in
This
principle
input drives
it
the
works in
animation
real
that's in
time,
the video shown on the
and then
left.
you can do it for voice
The
as well.
significant difference
I've
between
seen the
these methods
cases.
is the re-rendering of the math
And
interior. To this
yeah,
end,
other than that, I
researchers
don't know
assess the
what
math
would be the
interior of the
application for
target
this,
actor using video
but
footage from the training
but in
sequences
principle
and
it
rolling
works.
parametric.
Now you can play. It's a mask, and this kind of mask now is working. And again, again, if you think about it as a kind of computational problem, it's extremely hard, because you need to manipulate all of these pixels. But of course, the result is, I don't want to laugh at, for example, at this to make a fun of like, I don't know, Putin or Donald Trump, but it's amazing how it works. So there is no sound, I think, in principle. So you can check it out later. So if you are interested in this kind of, I think, new work that you can do a lot of things, and myself, I'm more interested in engineering applications, because most of these applications at the moment are focused only on computer vision, classical computer vision applications, or natural language processing. But I think there are infinite number of real world engineering questions, and for each of them we have disciplines. I mean, if you go to ETH website and then go to different departments and look what they are doing, I think there's enormous potential, and this is for me interesting. And if you find some other interest, we should go through this course material, which is not a course, it's a kind of seminars. And then I'm going to start in a step by step, and then with the codes, and usually no 100%, yeah, 90% Python codes. So you have the lecture notes, which is a runnable Python notebook. So we will start, for example, topics of determinism and scientific modeling, and then end of determinism, chaos, and so on, non-predictable determinism. This is one session, then one session on probability. Maybe we can skip this if you know it. One session on like the statistical methods and estimation methods, like kernel density estimations, and linear transportation. Maybe you have heard about PCA or data clustering. These are very generic techniques that it's everywhere in all of these applications. So self-organizing map that we have been working at Archer for the last 5-6 years. Markov chains, amazing and powerful method introduced by Markov in 1906. And this is for me the first data-driven model in the language. And as well, I think this guy is referring to him as well. But back then in his time, there were no computer at all, and computation was a manual work. And then he has this idea, a nice paper in 1906, but nobody listened to him. And later, in 90 years, this was the first application in Google PageRank, which worked because of the data. So this is one topic, and then again Markov chain with different approaches. And then we go to deep neural networks and autoencoders, and then different kind of autoencoders. For example, this kind of semantic labeling is a kind of autoencoder. Is a name. Just it learns to encode itself. So it learns to And then when you do that, you have this kind of vectorial representation, and then when you play with that vector, you can generate new faces, for example. This is the case. Instead of focusing on the picture itself, you convert your images, for example, if it's about face or it's about music or anything, you convert it to a space which is called latent space. And then in that space, when you do linear interpolations and you go back to the original space, you have a different face, for example, or different music, for example. So then you have this kind of ensemble models, which is amazing, and most of the competition are winning with these methods, which is to randomize your models, and it works perfectly. It's random forests, for example, or XGBoost, or many of them. And then I will try to focus, depending on your interest, on data-driven applications, in principle. But this will be more kind of a tutorial for how to use APIs, how to get the data from and different sources and so on, how to clean the data, and very technical things. And sometimes nowadays it's called data science, for example, or data hacking skills or this kind of thing. And then we go to Fourier analysis and signal processing, and then convolutional neural networks, which are, I think these are the best methods. Most of these applications that I showed you for this semantic labeling of self-driving car, all of them are working just based on these convolutional neural networks. And these convolutional neural networks idea is from 1980s, and it didn't work. And of course there are lots of tricks now it's working, but many say it's because of it was because of use of GPUs and more data sets. Other than that, the techniques are like 30 years old, and nobody was looking at them, for example, for 30 years. So then we have recurrent neural networks, which are amazing. These are very good methods. I think for me, these two methods are amazing. These are most of the applications, successful applications, are based on these two concepts. So there are lots of varieties, no? But you need to learn what is the concept and what's about. And here, for example, it's about learning sequences. This sequence could be anything. It could be time, it could be music, it could be a graph, anything. It could be an image. For example, you say one row of the image to the other is a sequence. So you can learn anything sequential. So you need to learn this sequential dependencies. In convolutional neural network is different because you need to learn some kind of invariances in some kind of homogeneous data. For example, if you have a picture, if you compare pixel by pixel, it's not working, for example. But when we visually look at the picture, you just say, okay, this is the same person in this picture, but the location in terms of pixel is different. So the convolutions are, and then convolutional neural networks, which is a hierarchical model, learns these kind of invariances. And it's amazing because most of the applications are just images and so on, these kind of signals, but conceptually, I think in future we will see amazing applications that we don't know yet because they're so powerful methods conceptually. So then we will talk again about recurrent neural networks, and then at the end I will talk briefly about reinforcement learning, which is again becoming a hot topic. And this was mainly my master thesis around 6-7 years ago, but that time it was not based on this deep learning, it was kind of rule-based reinforcement learning. So this was it for today, and then I will think about it. It's not necessarily sequential, but next week will be about one of these sessions if you are interested to attend. So of course I will show some applications, but it will be mainly about the concepts and techniques. So if you learn it, so you can start playing with that. So thank you. And now if you have questions, please. And if not, then thank you. I hope to see you soon.